Hello there, guys. I'm going to try and explain the tricky logic of when you subtract from one in probability and when you don't. And the truth is, you know, there's no simple answer to it. And oftentimes you can do it or you can do it a different way. And that both helps and maybe hinders a little bit. But I will explain it in greater detail here. And I'm sure you'll at least understand more why there is that kind of peculiarity of why you could do it or not do it, depending on almost on preference. Okay. So I'm going to show you two questions, both from 2021 to start off. I'm going to go through them fast because we have looked at them already as such. We've already done the questions. But type O, people with type O blood represent 8% of the population. At a blood donation clinic, 10 donors give blood, one after the other. Find the probability that the 10th person is the third O negative donor. So in this case, if I simplified this down slightly and I said, what's the probability? If I said, what's the probability that exactly two from the first nine donors are type O and the 10th donor is also type O. Now that is the question. Okay. Now it is going to be a Bernoulli trial question because as I phrase it here, as I say it, it would use the word exactly. So it hasn't said that in the question, but when we look at the logic, that's what it means. Find the probability that exactly two from the first nine donors are type O and the 10th donor is also type O. So for this reason, it is Bernoulli, but we're looking at the first nine donors. We're saying the probability of success, when we're talking about the success, it is being a type O, and probability of failure is being not type O. I'm not type O myself. I don't feel like a failure, but that's the way the question is. So here is the logic. It is from the first nine people. The, the probability of exactly two successes is 0.922 times 0, and I can have that as a C as well. 9 choose 2 times 0.08 to the power 2 times 0.92 to the power 7. But then it's multiplied by this. This is the 10th donor is type O. The probability of that is 0.8. That gives us the exact thing that's described, and it turns out the answer is 0.0103. Okay, no need for subtraction there at all. At the blood donation clinic, 5 donors give blood. What's the probability that at least one of the 5 donates type O? Now, when you see the at least one, it's hinting at the fact that you could be subtracting, but you don't always have to, okay? And you don't ever have to, in fact. But oftentimes it can save you a bit of time. So the probability of our successes from N trials, again, is Bernoulli, right? But when it says at least one from the 5, I could have 1 or 2 or 3 or 4 or 5. And I could do 5 different Bernoullis and add up them all together. And that would give me the correct answer. But because it's saying at least one of the 5, well, then if I think about my 5 trials, my success, my failure, and if I work out the probability that there's no success, well, the probability of at least one is equal to 1 minus the probability of none. Okay? So if I work the probability of no successes, 1 minus 5 choose 0 times 0.08 to the power 0 times 0.92 to the power 5. If I work that out, the probability of no successes and subtract it away from 1, I will get the right answer. Now, as I said, why I do this is because I only do one Bernoulli trial and subtract it from 1. I could do 5 Bernoulli trials and add them together and I would get the exact same answer. Okay, So that is one scenario where you do use it. You can use it. It makes sense to use it. The start, that was the last question in 2021. This is the first question in 2021. In a particular population, 15% of the people are left-footed, players, or left-footed people, I suppose. On a soccer team with 11 players, including the one goalkeeper, is picked at random from the population. Find the probability there's exactly one left-footed player on the team. Well, this is the easiest type of Bernoulli. The word exactly gives us the hint that it is Bernoulli. We have n people in our trial. Probability of success is 0.15, probability of failure is 0.85. 11 choose 1 times 0.15 to the power 1 times 0.85 to the power 10. Put it all in, get my answer, and that is the probability of having exactly 1 from 11 people are left-footed. 15 marks. Pretty generous. Find the probability that less than 3 players on the team are left-footed. So again, you might be thinking, okay, that might be a case where I'm going to use 1 minus. However, in this case, I have 11 people and I'm saying less than 3. So that's 2 or 1 or 0. Okay, I can do it the other way around. 0 or 2 or 1. Now, if I wanted, I could say 1 minus the probability of 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11. And so I could work out, I could do, let me see how many there'd be. 1, 2, 3, 4, 5, 6, 7, 8, 9 different Bernoullis, add them all up together and subtract away from 1. But this way here, I can do just 3 Bernoullis, so less than 3 players. So I work out the probability of nobody being left-footed. Okay, I work out the probability of 1 person being left-footed. And I work out the probability of 2 people being left-footed. And when I work out the probability of 0 people being left-footed, 1 person being left-footed, 2 people being left-footed, and add them together, I get my answer 0.7787. So I don't need, and the correct two decimal place 0.78, so I don't need to subtract from 1 there. As I said, I could do it this way, get those 9 different Bernoullis and subtract from 1, but why would I? That would just be creating me extra work. Okay, I'm going to now get another one of these, slightly different kind of variation again, and we'll look at what we would do in that case, okay? And over time, what I'm hoping you'll see is, well, you could try it this way and see does that work. You could try it that way and see does that work. And remember, there's no such thing as negative marking, so you can try it the 2 ways. So we're back here looking at Olga, right? And you can, you can stop, pause the recording here and do it yourself, right? See how you get on, right? But again, I'm going to go through this fast because we've done it, right? It's about the circular spinner with the 12 sectors. 5 of the sectors are €6. 3 of the sectors are €9, and the rest are €0. In this case, it says she plays the game twice. Find the probability that she gets less than €16 in total. Give your answer. Now, I'm going to use the 1 minus in this case, but I don't have to. I could work out the probability that she gets €0 and €0, which would be €0 in total. I could work out that she gets 0 and 6, which would be 6. I could say 6 and 0, which would be 6. All right, that's 3 possibilities. I could work out the probability that she gets a 0 and 9, which would be 9. 9 and 0, which would be 9. I could work out the probability she gets 6 and then 9, which would be 15, and then 9 and then 6, which would be 15. So I could work out all of those probabilities. Okay, work them all out, add them all up together, and I get an answer. That would be the probability that she gets less than 16. Or I can work out the logic that the only way she can get more than 16 is if she gets a 9 followed by a 9. €18 in total. So I work out the probability that she gets a 9 and a 9, and I subtract that away from 1. And since that's the only possible way she can get more than €16, If I subtract that probability away from 1, I'm going to get my answer. So it's 1 minus 15 over 16, which is the 0.9375. Okay. So again, that was a scenario. You can do it in more than one way, right? You can do it the other way, but sometimes it's just saving you time. Okay, let us move now to a different one. And I'm going to do one more of these, and then I'm just going to show you the Z-score one. Again, you can pause here now and try this question yourself. But John bought a car a number of years ago. The table below gives an estimate for the probability that each of the following three events happens to John's car in the next year. So the event is the head gasket blows. Probability of that happening is 0.095. The probability the timing belt goes 0.041, and the probability the air filter breaks 0.073. Now, the first thing is, before I do anything else, I could work out the probability those events do not happen, which again is again I'm using 1 minus, right? So it's the kind of most simple case of this. The probability of that not happening, first one is 0.905. That's just a coincidence that those numbers look similar. If the probability of the timing belt going is 0.041, the probability of not going is 0.959. And if the probability of the air filter going is 0.073, the probability of not going is 0.927. Okay? And then it says work out the probability that at least one of these events in the table would occur. Now you could work this out. You could work out the probability that the head gasket goes, but the other two don't. You can work out the probability that the timing belt goes, but the other two don't. You can work out the probability that the air filter goes, but the other two don't. And you could add those together, you will get your answer. But if you do this, the probability that at least one of them will go. Actually, didn't I just bloom and say the wrong thing there? Because that wouldn't have fully captured it. You know? And I guess this is the beauty of it. You know? I could go back and edit that out now and say, oh yeah, geez, I'd never make a mistake. But there you go. As I always say, probability can make a fool of you. I was just about to say the wrong thing. But actually, what I outlined was not the full answer. So let me just call that H, T, and A, right? So I was saying H, but not T and not A. But that's not quite right. Because, of course, it could have been that the head gasket blows, the timing belt goes, and the air filter doesn't. Or it could have been the head gasket goes, the timing belt doesn't, and the air filter goes. Or it could have been all three of them, you know? So it could have been all of them went. So there's actually lots of possibilities there, right? But to take them all into account, right? I'm kind of just kind of looking at the probability, the probabilities of it all, and like the permutations of it all in my head. But the simplest way to remove all those permutations is to say the probability that at least one of them happening is 1 minus the probability that none of them happens. And I can work out that very, very easily. 1 minus the probability that none of them happens, well, the probability that none of them happens is the, to my color coding here again, is the yellow times the green times the orange. And I know we kind of don't fully need it, but if we put in the brackets there, the probability that none of them happens is 0.804538. I take that away from 1 and I get my answer of 0.195, correct to 3 decimal places. So I think that's a very good example because it, we use the 1 minus in the simplest sense here and in a more complicated way down here. So that would be the answer for that part. Now, I'm going to go to Z-Scores just to show you how it links in with Z-Scores as well, because that's a little bit different. In all these cases here, I could have used it, the 1 minus, or wouldn't have to. I could do it a different way. But with Z-Scores, sometimes you just basically have to because of the way the table book is created. So this is kind of last bit we're going to do here. There's a few parts to this, right? And you can pause again each time. Okay, so in an athletics competition, there are a number of heats of the 1500-meter race. In the heats, the times that it took the runners to complete the 1500 are approximately normally distributed, indicating the bell curve, with a mean time of 225 seconds, which is going to be our mu, and a standard deviation of 12 seconds, which is our sigma. Find the percentage of runners in the heat who took more than 240 seconds to run the 150 meters. Now, people often ask, is this section probability or is it stats? Well, it's kind of both, because you can say find the percentage and it's going to be looking like a statistic, but it's also kind of finding the probability that any one runner selected at random will take more than 240 seconds. Now, we don't have the stats on this type of running, right? But we do know about normal distribution. We know about the page 36 and 37, which give us the probability values for the standard normal distribution, mean zero, standard deviation of one. And we have this standardizing formula on page 32, which allows us to go from scores like this one to do it kind of running into normal distribution values. So z is equal to x minus mu over sigma. In our case, mu is 225, sigma is 12, and our x in this case is going to be 240. And so what that is saying is the z-score that corresponds to that is 1.25 standard deviations. So here somewhere, right, we have this z-score. So the x-score is 240 seconds, and the z-score is 1.5 standard deviations. Again, where would that be coming from? It'd be coming from a situation where the mean is equal to, like the mean in this case is 225, but the mean of the standard normal distribution will be zero. Now, what we're asked to find is what's the probability that anyone selected at random would run a time greater than 240, which is the same as saying, what percentage of the curve is to the right of that z-score. But the truth is, I can't work it out straight away because these values on 36 and 37, the numbers in the kind of main body of it relate to the probability or the percentage of values that are to the left of that curve rather than to the right of it. That's just the way it's designed. So I can't work out that little region in red directly, but I can work out the region in orange. And how I do it is I say the probability of a z-score being greater or equal to 1.25, let me keep my coloring the same, the probability of the z-score being greater or equal to 1.5 standard deviations is 1 minus the probability of it being less than 1.25. So I calculate the 1.25 on my page 37. 1.25, there it is, 0.98944. I subtract that away from 1 and I get 0.1056, 10.56%. So what we're saying here is that basically 89.44% of all the runners will be less than 240 seconds and 10.56% will be greater than it. So I had to use 1 minus in that case because I just couldn't work it out otherwise. Okay, let's keep going. 20% of the runners with the fastest times qualified for the finals. Assuming that the races were normally distributed as described above, work out the time needed to qualify for the final. Give your answer correct to the nearest second. Well, in this case, we're talking about, again, 20% of the fastest time. So again, we're talking to the right-hand side of the bell curve. But we actually have to be very careful with the way we describe that. So it's 20% of the runners with the fastest times qualify for the final. Now, the fastest sounds like, like say the tallest or the ones on the right hand side. But actually, when you think about the fact that we're talking about times, the fastest times will actually be the lowest amount of seconds. So it's on the left hand side. So again, we need to be very careful with this one, right? So where the one minus will come into play in this case is you're saying, well, there's 20% of the people will qualify, 80% of the people will not qualify. So you just got to be a bit careful with how we actually work this out, right? So in this case, right, there's a couple of little bits to this, so you have to kind of stick with me, right? But the nature of the bell curve, if there was 20% of people in one region and 80% of the people in the other region, well, when I'm looking up a z-score value, it'll be this side of it. So if I'm looking what z-score would allow 80% of the people to be on the left of it, if I look for 80% inside here, there's an interesting little point inside here as well that I'd be looking for 80%, right? And remember, the numbers inside the body of it are the percentages, the probabilities, right? So where I'm coming from here is 0.84 or 5, right? Now, some people could be inclined to go for the 0.8023 because it says 0.80, so 80. But this one here is actually closer. Now, there's a debate about this, and there isn't one accepted answer. So the reality is if you kind of go with either of these, you're likely to be right. And if you average it out, you're likely to be right as well. But I'm going to go with the one that's closest. Okay. So I'm going to go with the Z score being 0.84. Now, you just have to be a little bit careful. This is kind of H1 logic here, but we are talking about a negative Z score in this case because it is the fastest times. So we are to the left because like this would be the longer it takes you, the further to the right should be. Okay. So bear with me on that one anyway. Just take my word for it that it would be a negative Z score. So the negative Z score in this case is the minus 0.84. We have the X is what we're looking for. Mu is 225. Sigma is 12. We work it out and we get a value of 214.92. Now here's what I'm going to say to you. If you're not sure about that, like if you're thinking, God, I don't know about that one, what I'm going to say is go from the start as if you had this and try and figure out the Z score that relates to it. And you'll see that it's right. Okay. The very last bit we're going to do here is the following. Very last one. So Sally takes part in a number of different races in the competition. The probability that she makes a false start is 5%. Find the probability that she makes her first false start in the first race. Okay. So again, where does one minus come into it? Just in the very simple case, the probability of a clean start is 1 minus the probability of the false start, 0.95. In this case, we're given a very specific order. Clean start, clean start, clean start, false start. Okay? And that was my answer to the question for 5 marks. Okay, we see the at most here again. 20 relay teams took part in the competition. For any particular team, the probability that they drop the baton at some point is low, 0.1. Find the probability that at most 2 teams drop the baton during the competition and give your answer correct to 4 decimal places. So we could, we'll look at the simplest way. At most 2 means 0, 1, or 2. At most 2. So I can work out the probability that 0 teams drop the baton. I can work out the probability that 1 team drops the baton and 2 teams drop the baton, add them all up together, and I get my answer correct to 4 decimal places. Now, if I really wanted to use the 1 minus, I could work out the probability that 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20 teams drop the baton and subtract that away from 1. But the reason I wouldn't do that is because it would take me loads and loads and loads more work. I could do it, but I wouldn't. Okay, on that note, we will leave it there. We see that there's in the Bernoulli trials, if you're to use the 1 minus, you can always use something else. But in the Z scores, you have to use the 1 minus at certain times. And so while it's not simple, I hope you're kind of reassured that there's different ways to do it And if in doubt, do it twice. And you're going to get your best answer. Your best answer will be the one that you're awarded for. Okay, we'll see you online tonight.